festive topic to end the year. Software everyone hates. I'm Chris. I've worked in software for about 12 years, so that roughly puts me on still not really knowing what I'm doing. But in that time, I've worked for some pretty big businesses, and they have big systems, and they have lots of legacy systems as well, and everyone hates them. But just to be clear what legacy systems are, they're systems that are still providing some kind of value to the business, which is why you can't just delete them. But for whatever reason, they've gone to a state where you can no longer change it, or at least it's very expensive and hard to change them. So for example, I worked at a big publisher, and we worked on some projects to replace some of these systems. And we felt like we executed them brilliantly. We had parties about these projects, and we were all really happy about it. I decided to leave for a few years and then come back. And now these projects are described as horrible legacy systems that everyone hates. And I sort of heard like the Lion King circle of life in my head. And I realised that all I'm doing is just building legacy systems over and over again. And that's all we're doing. This is the part where I kind of backtrack a bit on the title. I can't actually do a talk about how to utterly prevent building legacy systems. But what I'm going to talk about is how unit tests can help keep your system malleable over time. But we're also going to talk about how unit tests can actually have the opposite effect and actually make your systems harder to change. So it would be fair to say that a lot of people in software are working on replacing legacy systems, and people are picking Go to do that, and that's great. One of the great things about Go is its stated simplicity, in that you can write some Go code and come back to it in 6 months' time, and it still broadly makes sense. And that's because of like the sort of very restricted syntax and features around the language. If I contrast it to my previous experiences as a Scala developer, I'm not going to slag off Scala, but at the Scala meetup, I did a talk with my friend called Scala, Just Enough Rope to Hang Yourself. And that went down really well. What really blows my mind about Go is the backward compatibility promise. So, given it seems like in the future Go will have generics, the idea of being able to take a project that I've worked on 5 years ago, check it out, and then refactor it to use generics with very little resistance seems like a really good thing to me. And that speaks to me in terms of Go being able to live a lot longer than perhaps other programming languages. And I have a Java update appearing over my speaker notes. So I promise I didn't make that up. So Manny Lehman was the head of computing at Imperial College London, and he was an all-round clever guy. And he created the laws of the laws of software evolution. What he's basically talking about are the forces that drive systems to change and the forces that stop us from changing software. This particular law, the law of continuous change, is talking about how, as a system lives in its environment, that's when we learn how it has to change. So, in short, what it's saying is that the needs of customers and users change over time. So, if you think about it, the likes of Facebook and Twitter, they don't have a Facebook project that they're going to finish in April and then have all the engineers move off and do something else. In order to keep Facebook and Twitter relevant and hopefully, well, I guess for them, hopefully keep everyone on their platforms, they have to keep evolving the software. But given this knowledge that we kind of all know that we have to keep iterating on software, I sort of find it interesting that there's so many processes and teams that are really focused on that first release in terms of doing lots of upfront planning and designing and thinking about your story points and all that kind of stuff, with the kind of imagination that once we've deployed it, we're all done. But as Lehman says, we only start learning how a system has to change once it's in its environment and it's being used by real people. But the good news is this is actually how we get to the true value of software. The fact that we can evolve systems as they live in their environment is what sets us apart from every other industry. This is also why it's difficult, because we have to apply these unpredictable changes to software, and that's obviously much harder than just starting from a clean slate. So even if you're some genius, rock star, guru, whatever developer, and you somehow write perfect software for the requirements that you're given today, it almost doesn't matter, because over time your designs will be challenged and they may be proven wrong over time. So the reality of software development is that you will be wrong as time goes by. And no amount of upfront planning and architectural gymnastics can save us from this. This is why phrases like "you ain't gonna need it" are really important, because it's basically just saying it's too hard to predict the future, so don't try and over-engineer things. What we really need to do is try and embrace this uncertainty and try and optimize for making our software as malleable as possible. As if the first law wasn't difficult enough, he also coined the law of increasing complexity. And what he's saying is, as a system evolves in its environment, it will become more and more complex unless you do effort to maintain it. So what he's saying here is you can't just take a system and keep piling features on and on and on and expect it to live. And in my experience, that's how I've seen a lot of systems slowly become this mess that's just impossible to change. So to deal with that, we must be able to continuously refactor our code so that we can manage this growing complexity, so that we can express the code as best we can. But what exactly is refactoring? It's a sort of phrase that's thrown around quite a lot. And in my experience, I hear people saying they're refactoring and they're really not. Martin Fowler talks about some individual who says they've been refactoring, but the system has been broken for days. And he's saying that's not refactoring. So what is refactoring? I find this super interesting, I hope you will too. So refactoring comes from the term factorisation from maths. So given the expression a half plus a quarter, how do you figure it out? Well, what you do is you factorise the denominators so that they're equal. What that lets us then do is just add them up nice and easily. But what's interesting about this is these two expressions both mean the same thing. We haven't actually changed the meaning of the expression, it's still the same, but what we've done by factorising it is make it easier for us to work with. And that's exactly what we should be doing when we're refactoring our code. We're just simply re-expressing it to make it easier to understand and to work with. The important bit here is that when you're refactoring, you're just changing the way the code is expressed, but you mustn't be changing behavior at the same time. So we've got some codes. So here's a simple hello function in Go. It takes the name of the person to greet and the language to greet them in. And let's just pretend there's like 20 languages in there. And each time it's doing it, it's going, if it's this one, say hola. If it's this one, do French, etc. In my opinion, I wanted to refactor it. So what I did was I refactored out the figuring out what the greeting is from the language code from the string concatenation. This is a really simple, this is a simple refactoring, but nothing says refactoring can't be bigger than that. You could introduce interfaces, new structs, 10 functions or whatever. It's still refactoring so long as you're not changing behavior. And I really want to emphasize this. Like, if you are refactoring the code and change behavior, you're doing two things at once. And that's how we arrive at this, in these states where people saying they're doing refactoring in days on end, and they often fail because they just get into this rabbit hole of trying to change too much stuff at once. This is the sort of thing that Fowler was referring to. You're not refactoring if you're changing the behavior and changing the way the code is expressed. So how do we know if we haven't changed behavior? Even with our simple little function there, having to manually check that over and over again would obviously become a bit of a chore. And in a large code base, that just doesn't scale, right? So we need unit tests. What they're there to is to help facilitate refactoring. They will automatically verify that behavior is what you expect from your functions, and they're a tool to give us a safety net to do our refactoring. So here's an example of a unit test in Go. What's great about writing tests in Go is it's just plain Go code. So here I'm just calling my hello function and recording this result, and then I'm declaring what I want from it, and I just do an if statement, and if they're not equal, then I just call out to the error library and say there was a problem. To run the tests, you just do go test, and that will execute your test. And now this means I have this safety net to refactor my function as much as I like. So for instance here, I was doing some refactoring of our imaginary function and I made a terrible mistake, but thankfully the test told me before I ship it. And notice how, I didn't make this up, it's literally taking no time at all to run this test. So that's obviously way better than manually shipping. I assume it's some nanoseconds, but yeah, whatever. It proves my point, so I left it. So a good test suite should be giving us this immediate feedback when we're refactoring. So earlier I showed running a test through the command line, but in practice you'll probably want to find out what magic incantation keyboard shortcut there is in your favorite editor or IDE so that you can just run your tests as you refactor. And the important point you want to get to is just doing lots of small refactors and getting fast feedback loops so that you don't go into these rabbit holes of doing these big refactors which you then end up making a mess and having to revert it all. That's a bit low down there, but basically there's a screenshot there from a project I work on that has 700 odd tests, and I can just hit the magic button on my IDE and I get feedback on it in like 50 milliseconds. And that feels very empowering to me in terms of being able to refactor as freely as I can. So to summarize so far, software has to change to stay relevant, and we need to keep refactoring to manage the incoming complexity as it comes along, and tests should be helping us to refactor. Pause for refactor. So, if that's the case, if unit tests are so obviously brilliant, why is there sometimes resistance to running? In the code demo just now, I didn't see any tests being written. And you can go on the internet and find loads of articles about how unit tests are considered harmful and all that kind of stuff. But put another way, those projects I described that I worked on are no longer described in kind terms. Well, I totally wrote unit tests there, so that's a bit sad. So this, to me, is the riskiest part of the talk, because I hope you're all going to raise your hands and lower your hands to prove my point. So, raise your hand if you work in a project with a reasonable test coverage. Good stuff. Now keep it up. Now leave your hand up if you've never had to change your tests while refactoring. You know what you do. So shouldn't we be able to refactor without changing our tests? The whole point of these tests was they were supposed to free us to refactor, and now suddenly, every time I'm trying to change the damn software, a bunch of tests fail. It's like, this is the opposite of what they're supposed to be doing for us. Why are the tests impeding us? So I'm going to go for a fairly abstract example here. So bear with me. So someone has asked us to build a square. And we've decided the best approach to do that is to stick two triangles together. So our testing strategy is we'll write some tests to make sure the square is squarey, it's got the equal size and all that stuff. And now we're going to test our triangles work right. Because we want to have plenty of tests, and we want to get 100% test coverage. That says 100%, not 0% test coverage. Yeah, we want to have loads of coverage. And people like me stand up and say, tests are great. So yeah, let's write loads of tests. So we'll test that the sum of the angles in our triangles are 180 degrees, etc., etc. But remember our friend Manny Lehman. He said that software has to change. And quite often it's someone else doing the change. So a new developer's come along and she's evolved the software somehow, she's added new features or whatever, and now she's decided that actually it would be better if squares were made out of rectangles. So now she gets a load of failing tests, she's getting a load of mixed signals from her tests. She can't really tell she's actually broken the system, so she has to dive through these tests and go, is this thing actually important? Can I just delete this test? It's not actually important that the square is made out of triangles. But the tests that have been written against it have kind of elevated them to be more important than it actually is. And I can be sympathetic to how code bases sort of arrive in these kind of states, because, well, I've done it. When I first started learning about tests, I followed some simple tutorials like the one I just showed earlier, where you sort of see how to test, basic functions. But then you get to a point where it's like, oh, I don't know how to test this particular thing. So then you start learning about the sort of more advanced testing techniques like dependency injection and mocking and that stuff. And now you feel like a badass. You feel like you can test absolutely every damn line of code in your system. And you feel like you're making this bomb-proof software. There's no chance of anyone breaking the system because I've written a test against everything. But maybe building bomb-proof software isn't actually that great, because it's so bomb-proof that actually no one can change the code at all. So at this point, you feel a bit betrayed by your tests. You're like, I was writing these tests to improve my life, but actually it seems like it's making things worse for me. So you have a few options at this point. you can definitely cash in some internet points and write some other post on Reddit or whatever about how unit tests are considered harmful. You can do that. But maybe we can have a bit of a think about this. It's very easy to get a bit Lord of the Flies about tests. Like on the one hand, you have people saying, you know, you must write unit tests. This is how you get reliable, robust software, and so you can refactor it and all this kind of stuff, basically all the stuff I just said. On the other hand, you have people saying like, well, I tried this, and all it really seems to do is, you know, all these tests are now getting in the way, and I'm not even really sure that these tests are helping me at all. So when we're doing anything in software, we sometimes need to remind ourselves why we're doing it. I think people are losing track of why we're writing tests in the first place. We're writing tests so that we can automatically verify and document the behavior of the system. It is not about test coverage. A lot of the problems start when people are trying to make this bomb-proof software and testing every single facet, and God help these teams who actually have someone saying, your test coverage isn't high enough, and you desperately write all these tests. What we want to do is favour testing useful behaviour rather than implementation detail. We want our tests to tell us if we have broken important behaviours in our system as we evolve it. So that's what we need to be testing against. We don't want our tests to be asserting on implementation detail, because that's when they start to get in our way when we're trying to refactor and change the system. So our triangles from before is an example of testing at too low a level. It wasn't important that we use triangles to build a square, but as we said, the tests are now wrongly implying that it is important. And the result of this is every time someone wants to change something, they have a bunch of failing tests. So you might say, well, the natural conclusion is if we only want to test behavior, perhaps we should only write black box tests. So, for instance, if you're making some kind of website, you spin up the web server, some databases, some message queues, whatever, and then you fire up a headless web browser, and you automate it so it can run through your website as if it's a real user and then make some assertions. And these tests do have value in terms of checking these key user journeys, but they're not too helpful for refactoring. They're not that great at telling you the root causes of problems, and because they're slower to run, you're more likely to run them less often. And then we're back to the scenario of doing these big refactors for hours on end, and then running these end-to-end tests. And then at that point, it's the only point where you realise you've messed up. And another thing that these sort of black box tests often don't do is they don't really express the important rules of your domain as well as unit tests can. So I've got an example I've made up here where you got an account with $50, and if you try and withdraw more than $50, you get an overdraft warning. I would contend that even if you've never written Go before, you can probably understand the important business rule behind that. So what is the right level for unit tests? Well, it turns out it's actually a design problem. We need to be able to design our software in such a way so that we can write these meaningful unit tests. So I've been rabbiting on about tests for 19 minutes now, so let's just forget about tests for a moment. We want our code to have decoupled, self-contained, useful units of behavior so that we can build systems together. The way I like to think of it is they're like Lego bricks. If you can build packages that are like Lego bricks within your system, you can easily stick them together to build castles or banks or whatever. So once you have these packages or these units around these self-contained, relevant, real things, your tests, by definition, will be testing real things, because they're testing against a useful thing. But on the other hand, if you're designing your software in such a way that you have these units, they're a bit weird, they have a mixture of concerns, and they're not really self-contained, and they have all sorts of, they're concerned about all sorts of different things, it follows that your tests will also reflect that back to you. Your tests will also be weird. So in respect to Go, packages are a really nice boundary for unit tests, because the packages are like the boundary of useful behavior in your system. And they should be centered around something like a real thing in your system. And if you're designing your packages well, you won't be leaking implementation details to the outside world. And by doing that, that means that your tests have no chance of coupling themselves to that implementation detail. But in order to do that, when you write your tests, why did I put this down at the bottom there? But basically, when you write your tests, you should use the external test packages technique, so that you can only write tests against the public API of your package. So everyone loves the Go standard library, and it's because it follows these general software engineering principles of having units of behavior that are self-contained and decoupled from other systems. It's no accident that they're pleasant to use and that so many great systems are built from them. So use them as inspiration when you're trying to design your own packages around your real things. So for my own curiosity, I had a look at the standard library and looked at its tests around HP Client. Now when you use HP Client, you can just use it sort of out of the box without any configuration. But in practice, what you want to do is provide a transport so you can configure things like read timeouts and write timeouts and that kind of thing. So they've made the API quite open in respect to client. And then that also means that you can then test it with a mocked transport so that your tests are reliable and are not reliant on the network. So this is my interview for Monzo, I guess. so if I were a designer at a bank, that's pretty much it. I'd have a customer package, an account package, an currency package, and I'd have the tests around the public API for those things. Now, underneath those packages, hypothetically, there could be hundreds of functions and hundreds of types and loads of interfaces and all that kind of stuff. They're all supporting the public API, but I'll resist the temptation of testing them, because that's when you start testing against implementation detail, and that's when we're back to our testing our triangles scenario. And just to be clear, these are unit tests. There's a lot of misconceptions around unit tests and thinking that a unit test can only be around a single class or a function or a method or whatever. Unit tests were never about that. Unit tests are around units. And what I mean by units are these things that are decoupled and self-contained. Underneath them, they're allowed to have all sorts of things collaborating to make them work, but just don't test those guys. But sometimes you are concerned with implementation detail, and the only advice I can really offer at this point is just try and make sure there's clear separation between your important behavior tests and the implementation tests. And you can use the t.run thing or just put them in a separate file or whatever, but just try and make sure there's a clear separation. So I think in the past, a lot of the time I've seen tests that assert on a behavior and an implementation detail on the same test, and then it becomes quite hard to debug when they inevitably fail. So what I'm hoping is that these sort of facets of software engineering, they sort of reinforce themselves. So starting from refactoring, when you're refactoring, they give you signals about your tests. If you're having to do lots of manual checks, that's telling you your tests aren't helping you enough, that you've got some stuff that's not tested. Or on the other hand, if they're failing lots, then obviously your tests are not helping you. They're too coupled for implementation detail, for instance. And at the same time, unit tests free us to do refactoring without, it allows us to be bold about our refactoring because we know we won't accidentally break anything. Swinging round, unit tests help validate and document our designs, and a good design is easy to unit test. And finally, good units or packages, they're easy to refactor, and refactoring helps manage the complexity within our packages. But most importantly, the most important thing about our software is behavior, and all three of these things also help with this stuff. So the refactoring helps refine our behaviors in the way they're implemented. Unit tests verify the behavior, and a unit's design helps us define our behaviors. So the next time you're doing your refactoring, try and remember the strict definition of refactoring. So you mustn't be changing any behavior. So just try and re-express the code to make it better, and then listen to the signals that you're getting. Right? If you feel uncomfortable doing it, you feel like, actually I need to manually test this before I ship this, then think about what tests you could write to stop yourself having to do that all the time. And on the other hand, if you're doing refactoring and a bunch of tests are failing, think about, are these tests at the right abstraction level? Or actually, do they have any value at all? Every test is a liability, like any code. Think about what value it brings and just delete it if it's no good. I would also encourage you to try TDD, test-driven development. The idea of it is you add a new test for every behavior, not class or anything like that. Every new behavior, you write some code to make the test pass, and then you refactor. For me, what it really emphasizes is the fast feedback loops to validate your decisions, and it really acknowledges the lessons that Lehman and all sorts of other clever software engineers have figured out in the past. But for me, whilst it's called test-driven development, the most important thing to me about it is the emphasis on continuously refactoring your code. Rather than shipping a bunch of code over a month, then realizing you've made a mess, and then spending days or weeks trying to clean it up, it's far more sustainable just to keep doing small refactors as you iterate on your software. To that end, I have some content on the internets to learn TDD with Go. It's about 9 months effort. It's had loads of contributions from the community. It's in Chinese as well, which I think is amazing. I mean, I assume it's good Chinese, I don't really know. Anyway, it's 100% free and open source, so it doesn't hurt to take a look. And obviously, I appreciate contributions and feedback. So there are a few materials that sort of inspired me for this talk. Ian Cooper's TDD, Where Did It All Go Wrong? Really opened my eyes into how I was doing TDD a bit rubbish. If you're interested in those laws of software evolution that Lehman talked about, Nat Price's talk explores those ideas a bit more. And finally, the TDD by example book by Kent Beck. It's just a lovely example of how to do TDD and how to design software. And it's not an intimidating book. It's quite small. It's quite easy to get through. So to wrap things up, so the strength of software is that it can and must change, and often in unpredictable ways. But don't try and over-engineer everything and try and predict the future. Instead, just optimize for making sure you can change your code with confidence. Make sure you're constantly refactoring your code, and a good test suite will enable you to do that constant refactoring. But at the same time, keep an eye on your tests because they can actually get into a state where they hurt your ability to refactor as well. And finally, all of this is basically a design problem. If you design your software in such a way that makes it easy to write these tests, you'll be in a good place. There's my cat. It's not a gopher. Don't care. Thank you.